Hydrology is the scientific study of the movement, distribution, and quality of water on Earth and other planets, including the hydrologic cycle, water resources and environmental watersheds. Sustainability. A practitioner of hydrology is a hydrologist working within the fields of earth or environmental science, physical geography, geology or civil and environmental engineering. Hydrology subdivides into surface water hydrology, groundwater hydrology, and marine hydrology. Domains of hydrology include hydrometeorology, surface hydrology, hydrogeology, drainage-basin management and water quality, where water plays the central role. Oceanography and meteorology are not included because water is only one of many important aspects within those fields. Hydrological research can inform environmental engineering, policy and planning. The term hydrology comes from Greek, delta omega rho, hydra, water, and lambda omicron gamma omicron sigma, logos, study. History. Hydrology has been a subject of investigation and engineering for millennia. For example, about 4000 BC the Nile was dammed to improve agricultural productivity of previously barren lands. Mesopotamian towns were protected from flooding with high earthen walls. Aqueducts were built by the Greeks and ancient Romans, while the history of China shows they built irrigation and flood control works. The ancient Sinhalese used hydrology to build complex irrigation works in Sri Lanka, also known for invention of the valve pit which allowed construction of large reservoirs, aqueducts and canals which still function. Marcus Vitruvius, in the 1st century BC, described a philosophical theory of the hydrologic cycle, in which precipitation falling in the mountains infiltrated the Earth's surface and led to streams and springs in the lowlands. With adoption of a more scientific approach, Leonardo da Vinci and Bernard Palissy independently reached an accurate representation of the hydrologic cycle. It was not until the 17th century that hydrologic variables began to be quantified. Pioneers of the modern science of hydrology include Pierre Perrot, Edme Marriott and Edmund Halley. By measuring rainfall, runoff, and drainage area, Perrot showed that rainfall was sufficient to account for flow of the Seine. Marriott combined velocity and river cross-section measurements to obtain discharge, again in the Seine. Halley showed that the evaporation from the Mediterranean Sea was sufficient to account for the outflow of rivers flowing into the sea. Advances in the 18th century included the Bernoulli piezometer and Bernoulli's equation, by Daniel Bernoulli, and the Pitot tube, by Henry Pitot. The 19th century saw development in groundwater hydrology, including Darcy's law, the Dupuy-Thiem well formula, and Hagen-Poiseuille's capillary flow equation. Rational analysis began to replace empiricism in the 20th century, while governmental agencies began their own hydrological research programs. Of particular importance were Leroy Sherman's unit hydrograph, the infiltration theory of Robert E. Horton, and C.V. Thius's aquifer test, equation describing well hydraulics. Since the 1950s, hydrology has been approached with a more theoretical basis than in the past, facilitated by advances in the physical understanding of hydrological processes and by the advent of computers and especially geographic information systems. Branches. Chemical hydrology is the study of the chemical characteristics of water. Eco-hydrology is the study of interactions between organisms and the hydrologic cycle. Hydrogeology is the study of the presence and movement of groundwater. Hydroinformatics is the adaptation of information technology to hydrology and water resources applications. Hydrometeorology is the study of the transfer of of water and energy between land and water body surfaces in the lower atmosphere. Isotope hydrology is the study of the isotopic signatures of water. Surface hydrology is the study of hydrologic processes that operate at a near Earth's surface. Drainage basin management covers water storage in the form of reservoirs and flood protection. Water quality includes the chemistry of water in rivers and lakes, both of pollutants and natural solutes. See also oceanography is the more general study of water in the oceans and estuaries. Meteorology is the more general study of the atmosphere and of weather, including precipitation as snow and rainfall. Limnology is the study of lakes. It covers the biological, chemical, physical, geological, and other attributes of all inland waters. Water resources are sources of water that are useful or potentially useful. Hydrology studies the availability of those resources, but usually not the uses. Applications determining the water balance of a region, determining the agricultural water balance, designing riparian restoration projects, mitigating and predicting flood, landslide and drought risk, real-time flood forecasting and flood warning, designing irrigation schemes and managing agricultural productivity, part of the hazard module in catastrophe modeling, providing drinking water, designing dams for water supply, hydroelectric power generation, designing bridges, designing sewers and urban drainage system, analyzing the impacts of antecedent moisture on sanitary sewer systems, predicting geomorphologic changes, such as erosion or sedimentation, assessing the impacts of natural and anthropogenic environmental change on water resources, assessing contaminant transport risk and establishing environmental policy guidelines. Themes. The central theme of hydrology is that water circulates throughout the Earth through different pathways and at different rates. The most vivid image of this is in the evaporation of water from the ocean, which forms clouds. These clouds drift over the land and produce rain. The rainwater flows into lakes, rivers, or aquifers. The water in lakes, rivers, and aquifers then either evaporates back to the atmosphere or eventually flows back to the ocean, completing a cycle. Water changes its state of being several times throughout this cycle. The areas of research within hydrology concern the movement of water between its various states, or within a given state, or simply quantifying the amounts in these states in a given region. Parts of hydrology concern developing methods for directly measuring these flows or amounts of water, while others concern modeling these processes either for scientific knowledge or for making prediction in practical applications. Groundwater is water beneath Earth's surface, often pumped for drinking water. Groundwater hydrology considers quantifying groundwater flow and solid transport. Problems in describing the saturated zone include the characterization of aquifers in terms of flow direction, groundwater pressure and, by inference, groundwater depth. Measurements here can be made using a piezometer. Aquifers are also described in terms of hydraulic conductivity, storativity and transmissivity. There are a number of geophysical methods for characterizing aquifers. There are also problems in characterizing the Vado zone. Infiltration is the process by which water enters the soil. Some of the water is absorbed, and the rest percolates down to the water table. The infiltration capacity, the maximum rate at which the soil can absorb water, depends on several factors. The layer that is already saturated provides a resistance that is proportional to its thickness, while that plus the depth of water above the soil provides the driving force. Dry soil can allow rapid infiltration by capillary action. This force diminishes as the soil becomes wet. Compaction reduces the porosity and the pore sizes. Surface cover increases capacity by retarding runoff, reducing compaction and other processes. High temperatures reduce viscosity, increasing infiltration. Soil moisture. Soil moisture can be measured in various ways by capacitance probe, time domain reflectometer or tensiometer. Other methods include solid sampling and geophysical methods. Surface water flow. Hydrology considers quantifying surface water flow and solid transport. Although the treatment of flows in large rivers is sometimes considered as a distinct topic of hydraulics or hydrodynamics, surface water flow can include flow both in recognizable river channels and otherwise. Methods for measuring flow once water has reached a river include the stream gauge and tracer techniques. Other topics include chemical transport as part of surface water, sediment transport and erosion. One of the important areas of hydrology is the interchange between rivers and aquifers. Groundwater. Surface water interactions in streams and aquifers can be complex, and the direction of net water flux may vary spatially along a stream, channel and over time at any particular location, depending on the relationship between stream stage and groundwater levels. Precipitation and evaporation. In some considerations, hydrology is thought of as starting at the land-atmosphere boundary, and so it is important to have adequate knowledge of both precipitation and evaporation. Precipitation can be measured in various ways. Disdrometer for precipitation characteristics at a fine time scale, radar for cloud properties, rain rate estimation, hail and snow detection, rain gauge for routine accurate measurements of rain and snowfall, satellite, rainy area identification, rain rate estimation, land cover, land use, soil moisture. Evaporation is an important part of the water cycle. It is partly affected by humidity, which can be measured by a sling psychrometer. It is also affected by the presence of snow, hail and ice, and can relate to dew, mist and fog. Hydrology considers evaporation of various forms, from water surfaces, as transpiration from plant surfaces in natural and agronomic ecosystems. A direct measurement of evaporation can be obtained using Simmons' evaporation pan. Detailed studies of evaporation involve boundary layer considerations as well as momentum, heat flux and energy budgets. Remote sensing. Remote sensing of hydrologic processes can provide information of various types. Sources include land-based sensors, airborne sensors and satellite sensors. Information can include clouds, surface moisture, vegetation cover. Water quality in hydrology. Studies of water quality concern organic and inorganic compounds, and both dissolved and sediment material. In addition, water quality is affected by the interaction of dissolved oxygen with organic material and various chemical transformations that may take place. Measurements of water quality may involve either in situ methods, in which analyses take place on site, often automatically, and laboratory-based analyses, and may include microbiological analysis, integrating measurement and modeling, budget analyses, parameter estimation, scaling in time and space, data assimilation, quality control of data, see for example double mass analysis. Prediction observations of hydrologic processes are used to make predictions of the future behavior of hydrologic systems. One of the major current concerns in hydrologic research is prediction in ungauged basins, i.e. in basins where no or only very few data exist. Statistical hydrology. By analyzing the statistical properties of hydrologic records, such as rainfall or river flow, hydrologists can estimate future hydrologic phenomena. When making assessments of how often relatively rare events will occur, analyses are made in terms of the return period of such events. Other quantities of interest include the average flow in a river in a year or by season, These estimates are important for engineers and economists so that proper risk analysis can be performed to influence investment decisions in future infrastructure and to determine the yield reliability characteristics of water supply systems. Statistical information is utilized to formulate operating rules for large dams forming part of systems which include agricultural, industrial and residential demands. Modeling hydrological models are simplified, conceptual representations of a part of the hydrologic cycle. They are primarily used for hydrological prediction and for understanding hydrological processes within the general field of scientific modeling. Two major types of hydrological models can be distinguished. Models based on data. These models are black box systems, using mathematical and statistical concepts to link a certain input to the model output. Commonly used techniques are regression, transfer functions, and system identification. The simplest of these models may be linear models, but it is common to deploy nonlinear components to represent some general aspects of a catchment's response without going deeply into the real physical processes involved. An example of such an aspect is the well-known behavior that a catchment will respond much more quickly and strongly when it is already wet than when it is dry. Models based on process descriptions. These models try to represent the physical processes observed in the real world. Typically, such models contain representations of surface runoff, subsurface flow, evapotranspiration, and channel flow, but they can be far more complicated. These models are known as deterministic hydrology models. Deterministic hydrology models can be subdivided into single-event models and continuous simulation models. Recent research in hydrological modeling tries to have a more global approach to the understanding of the behavior of hydrologic systems to make better predictions and to face the major challenges in water resources management. Transport. Water movement is a significant means by which other material, such as soil, gravel, boulders or pollutants, are transported from place to place. Initial input to receiving waters may arise from a point source discharge or a line source or area source, such as surface runoff. Since the 1960s, rather complex mathematical models have been developed, facilitated by the availability of high-speed computers. The most common pollutant classes analyzed are nutrients, pesticides, total dissolved solids and sediment. Organizations. Intergovernmental organizations, International Hydrological Program, international research bodies, International Water Management Institute, UNESCO IHE Institute for Water Education, national research bodies, Centre for Ecology and Hydrology, UK, Centre for Water Science, Cranfield University, UK, EWAG, Aquatic Research, Zurich, Switzerland. Institute of Hydrology, Albert Ludwigs University of Freiburg, Germany, United States Geological Survey, Water Resources of the United States. NOAA's National Weather Service, Office of Hydrologic Development, USA, U.S. Army Corps of Engineers Hydrologic Engineering Center, USA, Hydrologic Research Center, USA. NOAA Economics and Social Sciences, USA, University of Oklahoma Center for Natural Hazards and Disasters Research, USA, National Hydrology Research Center, Canada, National Institute of Hydrology, India, National and International Societies, Geological Society of America, Hydrogeology Division, American Geophysical Union, Hydrology Section, National Groundwater Association, American Water Resources Association, Consortium of Universities for the Advancement of Hydrologic Science, Inc., International Association of Hydrological Sciences, Statistics in Hydrology Working Group, German Hydrological Society, Italian Hydrological Society, http://www.siihs.it, Nordic Association for Hydrology, British Hydrological Society, Russian Geographical Society, Hydrology Commission, International Association for Environmental Hydrology, International Association of Hydrogeologists, Basin and Catchment-Wide Overviews Connected Waters Initiative, University of New South Wales, investigating and raising awareness of groundwater and water resource issues in Australia, Murray-Darling Basin Initiative, Department of Environment and Heritage, Australia. Research journals, Hydrological Processes, ISSN 1099-1085-08856-087, John Wiley and Amp. Sons. Hydrology Research, ISSN 0029-1277, IWA Publishing, Journal of Hydroinformatics, ISSN 1464-7141, IWA Publishing, Journal of Hydrologic Engineering, ISSN 0733-9496, ASCE Publication, Journal of Hydrology, Water Research, Water Resources Research, Hydrological Sciences Journal, Journal of the International Association of Hydrological Sciences, ISSN 0262-6667, ISSN 21503435.